All right. Hello, everyone. My name is Immanuel, and I'm presenting together with my student Saehan a system called BitGourmet, which performs deterministic approximation. So first of all, what is deterministic approximation? Well, typically, if we are processing aggregation queries, we have two choices. Either we process all data to get exact results, or we process the data sample to get confidence bounds. But exact processing often takes too long, and sampling is problematic for aggregation functions like maxima that are sensitive to outliers, and more importantly, users may not always be okay with getting bounds that they can only trust on with a certain probability. And that has recently motivated deterministic approximation, where the goal is to generate deterministic bounds that are guaranteed to contain the true aggregation value. The hope is that we are still faster than exact processing, but we get better guarantees than the sampling. Now, in order to generate those 100% bounds, we cannot use a subset of rows because there's always a chance that we might miss an important row. So instead of that, what we can do is perhaps to rather read a little bit of data, just a few bits from every row in our table. From that, we can derive hard bounds on the values of specific rows, from which we can derive hard bounds on the entire aggregate, and that is the high-level approach that we are following. Now, the literature on deterministic approximation is comparatively sparse. Those are probably the two papers most related to our work. One of them is specific to time series. The other one introduced the concept of deterministic approximation and shows how to do this for single tables and single operations, but none of them is able to handle complex SQL queries as they appear in standard benchmarks. And in order to get there, we have to look into problems like how do we execute joins in this scenario, how do we connect multiple operations in a multi-step plan, or how do we prioritize between different bits from different tables. We address those challenges in BitGourmet. The first part of the title refers to the fact that we have a very specific storage layout. Whereas a row store stores data for the same row consecutively and the column store values from the same column, we store data about specific bit positions of specific columns consecutively, which allows us to access only those bits that we are most interested in. The second part of the title refers to the fact that we carefully select which bits to process, and as we will show later, that turns out to be crucial in order to get benefits from this approach. But before we go into the internals, Saehan will give us a little demo for what BitGourmet looks like from the user perspective.
BitGourmet supports aggregation queries with group bys and filters. On the left, users can select the aggregation function, aggregated column, group by columns, and filters. For this demo, we use a typical laptop and a data set about childbirths in the United States. Now we're calculating the average age of mothers from year 1985 to 2008, grouped by their smoking habits. As you can see, we are not using approximation for now, and it takes few seconds for the query to finish. To use approximation, users can use the slider on the top left corner to set the error constraint. The error is defined by the relative distance between the lower and the upper bounds. We set the error constraint to be 40%, and using approximation, the query finishes much faster. The black bar indicates the deterministic bounds, and they are guaranteed to contain the exact value. The log on the left shows you how many bits have been used during processing. We use only 1/7 of all bits. Now we set the error constraint to be 10%. It takes a little bit more time to finish, but produce better bounds. We use 3 more bits compared to previous execution. Let's retry exact processing one more time, and still it takes a lot of time to finish. By reading and processing fewer bits, BitGourmet is much faster than exact processing.
All right, that was BitGourmet from the user perspective. And as soon as the slide comes back on, I'm gonna tell you more about the internals. Good. So now towards the internals of BitGourmet. Let's see what happens internally when processing a simple example query. So let's see, we are taking the query over here together with a user-defined constraint on the approximation error. Now the first thing that BitGourmet does is to identify the tables and columns in the database that are relevant for this query. And for those columns, we select an optimal combination of bit positions that we want to read. So as a result of that, we will only know a subset of the bits in every field. Now, to simplify things, let's assume that we are dealing with positive integers here. Then based on the bits we know, we can associate each field with a range of possible values depending on how the unknown bits are set. Based on this value range, we can, for instance, evaluate the unary predicate d greater 5, and we can conclude for some rows that they certainly satisfy this predicate. For other rows, we can conclude that they certainly do not satisfy the predicate, while for other rows, even neglecting the possibility of null values, we will be unsure about whether the predicate is satisfied or not, because it depends on the bits whose value we do not know. All right? Good. So now we have an evaluation result for each row of S. And next thing we do, we want to join S with R, and assume here that the join columns are connected by a foreign key constraint. In that scenario, the first thing we do for a join is to create a hash table that associates keys in the join column with a status, indicating whether all associated rows satisfy the predicates, whether some of the associated rows might satisfy the predicate, or whether definitely none of the rows associated with that key satisfy the predicate. And we build that hash table with one single scan over S using the status update rules that you see here. And here we have the result for this example. The next step is that we look at the rows of R, and again we associate each row of R with a status value, indicating whether that row possibly or certainly joins with a row in S. For that we use the previously generated hash table. And this is the result. So all we're left to do now is to calculate the bounds on the aggregate. And in order to calculate the lower bound of the sum aggregate, we sum up over the lower bounds that we get for the value ranges in the aggregation column A, considering only those rows for which we are certain that they join with some rows in S. In order to calculate an upper bound, we consider the upper bound of the value ranges in the aggregation column, and we consider all rows that certainly or possibly join with a tuple in S. Now that gives you a lower and an upper bound on the sum over A, the result of this query, and we are guaranteed that the true value is contained within those bounds. Now this example only illustrates a small subset of the features of BitGourmet. We used a scenario-specific optimizer, which I'm going to discuss in more detail on the next slide. We have an execution engine that may dynamically change the representation of data during processing if we believe that it reduces execution cost. And for most operations, we have multiple operator implementations that are tailored to specific data representations. We also have a buffer manager. The buffer pool stores bit vectors, and our buffer manager tries to predict which bits might become relevant for the following queries in an analysis session based on the query history. So that is a high-level overview. Now, let's discuss a little bit about the optimizer. We are considering two metrics during optimization, the processing cost and the approximation error. And our goal is to minimize processing cost for constraints on the output error. In order to tune that, we consider two parameters, which is the set of bits that we will process, as well as the way in which we will process them, including dynamically inserted data transformations. Now, the dependencies between those parameters are highly non-trivial. For instance, if we keep reducing the number of bits that we read from hard disk, there will come a point where reducing the number of bits further actually increases processing costs, because evaluating the predicates actually becomes less effective if we know less bits, and we will have to process more rows that potentially satisfy the associated predicates. The BitGourmet optimizer takes that into account based on scenario-specific cost and error models, which are fed by a scenario-specific cardinality model, which is binary, as it estimates separately the number of rows which we believe we will be certain that they satisfy the predicates, and the number of rows which will possibly satisfy the predicates. We need to estimate both as they are processed separately. And that is fed by data statistics, which are also specific since they describe data at a granularity of single bits. That was a very high-level overview. In our experiments, we compare against exact processing and against sampling. I'm going to present a few first results. Here we are first of all comparing against an exact processing baseline on queries of the star schema benchmark here. And as you see, we consistently achieve speed ups of factor 7 in average. And when analyzing those speed ups in more detail, it turns out that they correlate quite well with the reduction in data size that we achieve by dropping bits, and that is to be expected. However, it's not sufficient to just arbitrarily reduce the bits that we read. We want to be very careful which bits we are processing. Now, in this figure, we are comparing for a fixed number of bits the impact of the bit selection on the error that we get in the result. We are comparing the error achieved by the bit selection proposed by our optimizer against the runner-up and against an average bit selection. As you see here, it makes a huge difference for the error that we select the right bits to process. We also performed user studies in which we asked users to perform exploratory analysis on a few large data sets. And as you see here, when we compare exact processing and the time by BitGourmet for an approximation error of only 10%, then we get even higher speedups than before. And this can be explained by the fact that users often issue sequences of similar queries, and we are typically able to store the data which is relevant for those query sequences in main memory, but only if we focus on the most relevant bits. We also compared against sampling, here comparing the quality of our 100% confidence bounds against 99% confidence bounds, and also comparing the amount of data that BitGourmet and LinkedIn need to process in order to get there using different sampling rates for the sampling baseline. And that comparison is not entirely fair, since our bounds have a stronger semantics, as it is deterministic bounds, but nevertheless, for many queries, we achieve Pareto-optimal trade-offs between the amount of data processed and between the quality of the bounds. And there's a few queries where we do particularly well when analyzing them in more detail. It turns out that they are associated with highly selective predicates where sampling becomes difficult. And beyond this, there's a couple of error cases that can happen when using sampling, but not when using BitGourmet. First of all, we observed several cases, various cases, where the actual value falls outside of the confidence bounds for the sampling baseline. Also, there's cases where groups that should appear in the query result are missed entirely by sampling, and both of those cases cannot happen with BitGourmet. So we believe that we realize an interesting trade-off between the guarantees on the result and between the performance that we achieve. We propose a couple of avenues for future work in the paper, some of which we have already taken care of. In the near term, we plan to work particularly on optimizing the physical design for deterministic approximation and on using deterministic approximation to reduce processing costs in the cloud. That was a BitGourmet, a two-part presentation. Thank you very much for the attention and for the patience, and now we look forward to your questions. Thank you.
Questions?
So
very interesting work. So there have been in the last years a few papers that propose all sort of like bit weaving and bit representation and so forth, right? And they're all good ideas, but of course each one of them proposes a different bit representation, right? I mean, what is the hope that the way you actually do this bit weaving, right, might combine with what other people are proposing for indexing, for machine learning, for different types of processing, because of course otherwise we end up like with indexes, right? You build an index for something that is not useful for something else, and you end up with 100 indexes, right?
Right, okay. So indexing would be another interesting avenue for extensions. Right now I believe the most related prior work in terms of bits is the one that we saw here. The difference to that is basically that we are able to process complex SQL queries. So there has been several works on leveraging single bits. Most of that work does try to still compute a precise result. So here we are getting additional speed ups by calculating only deterministic bounds. So that would be the main difference to most of that prior work.
When you are doing the selection of the bits, is there a high tendency to select largely the most significant non-zero bits? Is there more to it than just that simple rule of thumb in the buffer management technique that you propose?
Okay, great question. So there is. Which bits we want to select depends as well on the way in which that column is used in the query, as well as on the data distribution. For instance, if you have an equality, or if you have an inequality predicate on a column, for instance, then selecting the highest order bit might not be efficient if this is typically set to 0 in most cases. So it depends on the data distribution, and it also depends on what you want to do with that column. I mean, for instance, for for columns that are used in predicates in general, often pays off to use bits that have a relatively high entropy, which is one of the statistics that we are storing about those different bit vectors, right? If you have, for instance, an aggregate, I mean, especially I would imagine for a maximum aggregate, then you want to start with the highest order bit. But if you have, for instance, a sum aggregate, then it might actually pay off to select one of the lower bits if they are more frequently set to 1 than some of the others.
Thank you. Let's take one more question.
I don't see how this is going to work in a multi-user workload. I can see that if you have a single user system and all the queries have a similar characteristic to them, I can see this working. But if you're interested in 10% and I'm interested in 40%, then the bits you choose are going to be query specific and user specific, and I don't see how to keep track of this. I also don't see how this is going to work unless you have a monotonic field. And so I think this seems really brittle to me.
All right. So I have to say that first of all, we are focusing on the single user case for the moment. We're only focusing on analytical processing for the moment. So if you're talking about analysis for multiple users, I could still imagine that as long as users select a similar precision requirement, for instance, you can reuse the same bits for different users. I mean, whenever you have an error permission of greater than 0%, then we can always reduce the number of bits that we need to read from one specific user. And we can access those bits separately. So, I mean, there would be some interesting work to be done on how to get even higher efficiency gains to support multiple users. But even if those users issue queries separately, then this system should help to have to process less data than with exact processing.
I thought what you're doing underlying is you're just caching the bits, right? So wouldn't you have a LRE-like replacement policy for the bits and it will still work out?
That is also something that we are doing. The results that I presented here are actually cold start results. So here we are reading the bits directly from hard disk, and we are storing the bits separately. So if you only read a subset of bits, then this really means that we are reading less data from hard disk, right? So caching additionally provides us with speed ups, but okay, the results for the star schema benchmark were cold start, and then I showed the results for the user study. There we additionally benefit from caching.
Great, wonderful. Thank you.